Hello, my name is Hanjun Lee from ADAS Lab at Seoul National University. Today I will share about advancing mobile GUI agents, a verifier-driven approach to practical deployment. This is part of intelligent agents that can automate tasks on mobile apps through their graphical user interfaces. In this talk, I'll present the key ideas behind approach called Vidroid and how it enables more efficient and reliable GUI task automation. Let me start with an outline of the talk. I'll begin by defining the problem and landscape, why building GI agents for mobile apps is challenging, and specifically why they propose a verification-driven approach for such agents. Next, I will describe the system design of Vidroid, including its overall architecture and workflow. Then dive into how they train the verifier model, introducing a method called P3, pairwise process preference, training and human agent joint annotation strategy to gather training data at scale. Finally, I'll show evidence from evaluation how Widroid performs on benchmark tasks and discuss some limitations and future outlook. By the end, I hope you will see how turning an LLM into a verifier leads to a faster and more effective GI agents. Before getting into this approach, let's clarify what a GUI agent is in this context. We are talking about agents that can execute user instruction on a device UI. For example, you tell your phone, install WhatsApp Messenger, and the agent will simulate touches and typing to do it. This is different from traditional automation, which might use internal APIs. Here, the agent interacts with apps like a human user would through the screen. Theoretically, every user's command could be done by this way. The conventional approach for such agents has been largely API based or using script sequences, which doesn't generalize well across different apps. Recent research has instead turned to LLMs to power GUI agents. The LLM observes the app's UI and generate action to take. In other words, most GUI agents focus on action generation. The agent tries to produce the next actions like click this button from scratch based on the interface and the task. This has achieved some success in understanding UI context and performing sequential steps. However, as we will see, having the LLM freely generate action can be problematic in terms of real, reliability and speed. Let me introduce our idea. The core idea of Widroid is a paradigm shift. Instead of having the LLM generate actions, you have the LLM verify actions. In other words, they pre-enumerate a set of candidate actions from the UI, and the LLM's job is to answer yes or no to the question. Does this action help complete the task for each candidate? By doing this, the agent can select the best action without the LLM generating anything new. It just judges the options. This dramatically simplifies the decision the model has to make and drastically shortens the output it needs to produce, a simple yes or no. We'll see how this leads to both higher reliability and much lower latency per step. This figures shows a brief summarized result. As you can see, Voidroid AP model not only achieved highest task success rate over related models, but also shortened latency precisely under 1 second. In contrast, other models showed that 5 to 25 seconds required per step, which is not appropriate for real-time service. Voidroid model size also 8 billion, which can adapt it on mobile device rather than other LLMs, which is good. This work makes three main contributions. Discretized action space and a pre-filling only workflow. We define Actually, they define a fixed set of possible actions, including UI interactions and some basic operations, and a workflow where the LLM only verifies pre-filled candidates instead of generating. This structured approach lets the agents evaluate many options in parallel, making decisions fast by batch verifying candidates. Pairwise process preference, P3 training for the verifier. This is a specialized training strategy where we show the verifier model pairs of correct versus incorrect action at each step. Each step in a task is a process so that it learns to distinguish the correct action more sharply. This pairwise contrastive training greatly strengthens the verifier's discriminative ability. Next, human agent joint annotation strategy. They introduced a scalable data collection pipeline where an initial agent and humans collaborate to label steps in many task executions. The agents does a first pass of annotation and humans correct mistakes. This approach allows to efficiently collect a large-scale, fine-grained dataset of steps for training with minimal human effort per example. Together, these innovations enable practical deployment of the GUI agent is more accurate and significantly faster than prior approaches. As I will quantify later, this achieves state-of-art success rates with a near real-time speed. So now, let's put this in context with related work. There's been a growing demand for mobile control via natural language. People want to just tell their phone what to do. LM have recently boosted what's possible because they can understand UI text and layout and generate action sequences. Existing GUI agents can be grouped into few categories. First, text-centric approaches. These use LLMs to reason and act using text alone. For example, React and CA Act style agents break the task into listening steps and action step by step using the LLM's own chain of thought. They create a problem with the plans. It's all like AutoDroid and MobileGPT try to improve the LLM agents by providing it with offline task traces or demonstrations. They integrate some recorded sequences of actions, logs of how tasks can be done into the model's memory or prompt, so the LLM has example to follow. Multimodal two-stage approaches. These explicitly combine UI understanding with listening. For instance, UI tasks, area UI, uGround, or first perform some form of UI grounding. They use a vision or UI parsing model to identify interface elements or possible actions, and then use an LLM to reason or decide using that grounded information. It's like pipeline. First interpret the UI, then decide the next action with LLM. Each of these lines of work made progress, but there are clear limitations that motivated them. Relying on prompt or only lightly fine-tuning an LLM hasn't fully solved multi-step decision making. The model might do okay for one or two steps, but as tasks get longer and UI changes dynamically, they struggle. Even very strong model hits a performance ceiling in these approaches. So let's move on to the motivation section. So there are a few things motivate others. First, domain data shortage. Ground truth labels are scarce. Next, insufficient decisiveness in multi-step dynamic UI performance. In fact, the best existing agents on a standard benchmark only achieve around 50% test success rate, whereas human performance is about 80% on the same tasks. So there's a big gap. And on top of that, latency a serious issue. Many of these agents take many seconds, sometimes tens of seconds, per action decision. That's far from real time. Simply throwing a larger LLM at the problem like GPT-4 improved understanding, but did not break the 50% success barrier and still incurs high delay. Also, COT React could further increase accuracy, but it would cause a token explosion, which would worsen latency. Finally, we need add structure that improves accuracy and latency simultaneously. So let's zoom in on the core idea of Vidroid with its advantages. The tagline is LLM as verifier. Concretely, for each possible action X, we prompt the LLM with a question like, given the task and what's on screen, does doing X help to accomplish the task? The LLM answers yes or no, which we interpret as a score, and then we execute the highest scoring action. That's the basic loop we discussed. Why is this powerful? A few key advantages. First, small candidate set. On mobile, any given screen has only a handful of things you can do next. The average is on the order of around 20 interactive elements per screen, so the search space is small in each step. You are not dealing with an unbounded set of actions, which means the verifier only has to sift through a manageable list of options. The second one is verification is easier than generation. This is fundamental insight. Instead of asking the model to create the correct action out of thin air, which is hard because the space of possible actions phrased in natural language is huge, we ask it to judge given actions. It's much easier for model to recognize a correct action when it sees it than to come up with it from scratch. Essentially, we've turned the problem into a classification task, good vs bad actions, rather than a generative task. In fact, we found that even a powerful model like GPT-4 is more reliable as a judge than a generator for actions. Using GPT-4 to verify choices yields better results than using GPT-4 to directly output the action sequence. Third, low latency decisions. Because the LLM's output for each action is just a short yes or no, and because we can batch process all candidates in parallel, the decision making step is extremely fast. We also implemented prefix caching using the VRM library so that the common part of the prompt, the instruction and current state is computed once. And only the variable part, the candidate action is processed for each option. This gave them roughly a 10 times speed up in verification compared to naive sequential evaluation. The end result is average of 0.7 seconds per decision, which is an order of magnitude faster than prior agents that often took 5 to 10 seconds. So they achieved significant latency reduction without sacrifice accuracy. In fact, they improved accuracy. These advantages are what make the verifier-driven approach not just conceptually neat, but practically very effective. Next, I will discuss some challenges they had to overcome to realize this system, which will segue into specific techniques we developed like training the verifier and annotating data. I just simply say we or sometimes they, but I didn't write this paper anyways. So next, this in challenge part, when building Vidroid, they encountered several challenges that guided design. I want to outline them because they map to the solution what they introduce. First, complete action space. How do they ensure the agent's action space is comprehensive? They realize The agent must consider not just the obvious UI element interactions, but also invisible or implicit action. For example, pressing Android homes or back buttons, waiting for something to load, or confirming a dialog like allow or yes or no prompts. These are not visible on the UI trees in the same way, but they are crucial actions. Also, for things like typing text is not just one action. There's the content of the text to consider. They need to incorporate all these basic operations into the action space to form a clear, complete set of actions. Solving this was part of defining their discretized action space and workflow. Second, efficient verification engine. Even though they only have at most a few dozen candidates, if if our verifi- if their verification step was slow, the agents wouldn't be practically deployable. They need to be able to evaluate dozens of candidates with an LLM at high speed. This meant optimizing how they prompt and learn the model, which they address with batch prompting and caching, as I mentioned. 3. Verifier training. Perhaps the biggest challenge, if they take a pre-trained LLM off the shelf and use it as a verifier, how well does it do? It turns out not well at all. A small 8 billion model like Llama without training basically fails completely, zero success rate at judging the correct action in their task. Even GPT-4 zero shot only gets about 34 to 35 success on our benchmark. In other words, out of the box LLM don't know how to be good critics of GIA actions. They might be great general listener, but they are not calibrated to evaluate fine-grained UI actions in a sequence. So the other absolutely needed a dedicated training strategy to train the verifier models to this job. Dataset absence. To train such a verifier, they require a large number of examples of correct and incorrect actions at various steps, essentially a dataset of state candidates' action and labels correct or not. There was no existing dataset at the scale or granularity we need. Manually labeling the correct action at each step in thousand task trajectories would be prohibitively time consuming. They had to devise a way to collect step label annotation efficiently, which led uh, them to a human agent join annotation scheme. So these four challenges define the full action space, making verification fast, training the verifier effectively, and gathering trained data are what the next part of the work they talk will address. Each of their contributions is aimed at solving one or more of these challenges. Now I will explain the withdraw workflow step by step, which ties together some of those solutions. There are four stages in one loop iteration of the agents. 1. Action space extraction. The agent analyzes the current UI through Android's accessibility API. This gives a tree of UI elements and their properties. From this, they extract all possible user actions on this screen. These include typical interactions, tapping or clicking buttons, long pressing if available, scrolling lists, entering text into text fields, deleting text, and so on. But as I emphasized, they also always include basic operations that might not be in the UI trees. By adding these, they form a complete action space for the agent at that step. It's a discrete list of actions the agent can choose from. Think of it as a given the state. Here are, say, 15 things you could do next. Next, evaluate actions with the verifier. For each candidate action from step 1, we now call it a verifier model. They used a fixed prompt template that describes the task and current context, including a summary of what's been done so far and what's on the screen, and then ask about the candidate action. The only part that changes across the batch of the prompt is the description of the candidate action. Everything else stayed the same. This is where we leverage caching. The model processes the common part once they once. Then we quickly swap in each action to get a yes or no judgment. Our verification model is fine-tuned 8 billion parameter llama-based model that outputs yes or no, and internally they interpret that along with its probability as a score. After evaluating all candidates, the agent selects the highest scoring action as the chosen action for this step. Next, speed optimizations. I should note the optimization applied in step 2 to make it fast. Batch verification, meaning we run a bunch of those yes or no queries in parallel on the model. They also employ the VLM libraries automating prefixing caching, which is called APIs, which I mentioned. Cache is the forward path for the static part of the prompts and only computes the tail for each candidate. These together yield about a 10 times speed improvement over a naive approach where you run each candidate one by one. This is why our decision latency per step is so low compared to previous ones. They were really fully realizing parallelism and the short output lengths. 4. Action complete and execution. Now, once an action is selected, the agent needs to execute it on the device. Most action straightforward like click button X, they just dispatch that command to the emulator. However, a subset of actions require additional generation before execution. For example, if the chosen action is input text into field Y, we need to know what text to input. Or if the action is open app, we need to specify which app. About 20, about 12.4% of actions fall into this kind of category. For those, they do allow the model to generate the required contents. So for instance, if the task was send a text saying I'll be late, when the agent choose the action type into the messaging box, we have the model generate the actual message I'll be late to input. After any such completion, the agent executes the action on the device. Finally, after executions, the UI updates. The agents then update its working memory. As mentioned, they summarize the new state and what just happened. This update this updated context will be fed into the next iteration, and the agent goes back to step 1 to extract the next set of actions from the UI, and so on. The loop repeats until the task is finished. Either the agent selects the finish action or it reaches some end state of the task. That's full workflow. We've essentially covered how we handle the action space, how we do decision making via verification with optimization, and how we integrate a bit of generation for things like text input when needed, along with a memory mechanism. This addresses the first two challenges, complete action space and efficient engine. Next, we'll talk about how we train the verifier and how they gather data. Now on to training the verifier. As mentioned, using an LLM as a verifier without fine-tuning doesn't cut it. This slide explains their P3 training approach, where P3 stands for Pairwise Process Preference Training. The idea is to train verifier by giving it direct comparison between the correct action and incorrect ones at each step of task. First, let's understand why they need this special training. A zero-shot verifier has trouble separating the good action from the bad. The model's low probability scores for yes can be all over the place. They observed a high confidence spread across candidates. It might give somewhat high scores to multiple actions, including incorrect ones, because it hasn't run the fine nuance of what makes an action correct in a given state. In short, the model's judgments are not calibrate for our specific sequential decision context. So test context training is required. We need to teach the model with examples, which actions lead to success and which do not in various situations. Simples provides fine-tuning on good action whereas bad action is the direction, but they found that structuring it as a pairwise comparison at each step is especially effective. So how do they train the verifier? P3 training method work as follows. At each decision step in the task, they use the data to form pairs consisting of the correct action and one incorrect action. The verifier model is then trained to output a higher score for the correct action in each pair. Imagine we believe Imagine we have a particular state in the task where, say, the correct action was press the login button, but there were, for example, five other clickable things on the screen that would have been wrong to press. We will create training pair like press login with press cancel, press login with open menu, etc. For each incorrect alternative, we pair it with correct action. We then apply a contrastive loss that encourages the verifier to give a higher yes probability to the correct action than to the incorrect one. Essentially, we want score, we want make score larger, correct score larger than incorrect score, and we push the model in that direction for every such pair. If a step has n candidate actions, that yields n minus 1 pairs. This amplifies the learning signal because one step doesn't just give one example. It gives multiple pairwise example or the reinforcing which action is better than others. They also added one more clever twist to the training, which we call self-correcting training. This was designed to help the agent recover from mistakes during execution. The idea is suppose the agent did something wrong at a step, at say it entered the wrong text or navigated to the wrong screen. At the next step, I plus one, the best action might actually be a reversal action. Essentially, an undo or correction, like hitting back, going home, or deleting the text they just typed incorrectly. They want the verifier to recognize that in an error state, the correct action is one that corrects the mistake. To train this behavior, they take some erroneous state from our data state where the agent had made an error in the trajectory, and they labeled the reverse selection as a correct one for training purposes. For example, if in a training trace the agent went down a wrong path, at that point they labeled the go back action as a positive example, even though in the optimal trace maybe the agent wouldn't have been in the wrong state to begin with. But they are augmenting for the robustness. Similarly, if the agent entered the wrong input in a field, they label the delete last input action as a correct action in that erroneous context. By doing this, they teach the verifier that in context that looks like mistake, the preferred action is to self-correct. However, they have to be careful not to overdo this. Otherwise, the agent might become overly timid or keep undoing things. So they just sample only a small percentage, about 2.5% of error state to apply this augmentation. So combining the pairwise contrastive training and this self-correction augmentation, their verification is both discriminative and resilient. This addresses the training challenges. They ended up with a custom training 8 billion verifier model that knows how to judge action in context far better than any of the shared LM could. Now the last piece, data annotation. To train the P3 verifier, They need lots of state action pair labeled correct vs incorrect. Pure manual labeling is infeasible, so they use a human agent join pipeline. First, task, instru- task instructions. They collect tasks from public app descriptions benchmarks. An LLM turns these into concrete user-like commands a human reviews and edits for clarity and achievability. Next, execute and trace. They learn each instruction in an emulator, prototype agent, or semi-manual to get an execute trace. Screen plus actions that successfully complete the task. Each step in a successful trace defines the answer, correct action. Next, agent first pass. The agent and verifier labels each step. Take actions correct. Other candidates incorrect. Is fast but imperfect. Target human fixes. They use verifier confidence entropy to flag likely mislabels with a median entropy threshold. They catch about 76% of real errors, human only correct flagged steps, drastically cutting efforts. A fully labeled dataset of set action pairs ready for P3 training with agents doing the bulk and humans correcting the edge cases. Next, they iterate this loop to scale. They scale in rounds, letting a better verifier enable cheaper data growth. Round 1 around 9K steps, more human effort to train the verifier. Round 2 around 27K steps as a verifier improves, fewer fix. Round 3 55% steps, human load drops further. Finally, round 4 around 110K step total verifier is strong, correction are light. Across round, the agent's annotation accuracy rise and human intervention falls. The entropy-based error detector's age improves as the verifier gets better at knowing when it is unsure. The verifier downstream performs scale roughly linearly with training data size. So we have some takeaway here. More data, better verifier, cheaper. Faster data, even better verifier. This feature this featureless cycle let us surpass around 100K decision points without prohibiting labeling cost. With the system built and the verifier trained, how does Breedroid actually perform? Here I will summarize the key evaluation result. So benchmark, they evaluate on three benchmark of mobile test automation. Android World, Android Lab, Mobile Agent Bench. Metrics, the primary metrics are success rate, the percentage of tasks the agent completed successfully within a time step limit, and latency. They use baselines for the text multimodeling, ground families, release LLMs like GPT-4o, DeepSeek R1, etc. Now the result, the key points. When it comes to success rate, Voidroid achieved the highest success rate on all three benchmarks. About the decision latency, they also greatly outperform others in speed. Their average decision-making latency is around 0.7 seconds per step. But there is one bottleneck, memory update. One finding is that their biggest remaining bottleneck is the working memory update step. Currently, after each action, they call GPT-4 to summarize the state, which is called reflection. This contributes a chunk of that 3.8 seconds full step latency. GPT-4 is slow. They tried replacing GPT-4 with smaller, faster models or simpler approaches like just logging the last screen text without a summary. They made things faster, but interestingly, it caused a big drop in success rate. With no proper memory, success fell from 59% 59.5% to about 40%. And even using a rule-based simple summary, it was about 46%. So the agent really realized one good high-level summary of what's happened to avoid getting confused or repeating mistakes. This tells us what while we want to remove GPT-4 for speed, we, we need to replace it with something comparably effective as summarization. Maybe a fine-tuned smaller model could do it in the future. Maintaining that memory of context is essential for high performance. Overall, the evaluation shows Withdraw is both more effective and more efficient than prior agents, achieving higher success on all tasks and doing so with much lower latency per step. It's a strong indication that the verifier-driven approach is better paradigm for this kind of problem. Before concluding, let's talk about the outlooks and what's next. One important observation from our work is regarding scalability. The success rate of Widroid rise roughly linearly with more trained data. They saw this during the iterative annotation when they increased the trained data set from 9K to 27K to 50K to 110K steps. The verifier's performance kept improving in a near linear trend, and it hasn't flattened yet at 110K. This suggests that if they continue to gather more diverse task data, they can expect further gains. In fact, on one benchmark, they saw success go from as low as around 50% with the smallest data to 59% with full data, and presumably with even more data it could approach or exceed human level over time. So data scaling is a clear path to make the agent even stronger. In summary, Widroid shows that by constraining an LLM to verify a role and backing it up with the right training and data, they can break past prior performance ceiling and achieve something closer to practical virtual assistants for GUI tasks. They get the benefit of logical judgment from the LLM while avoiding its verbosity and unpredictability. This approach scales with the data and compute, so it should only get better. They are very excited about this result and potential to deploy such agent in your scenario soon. So this is all about my presentations. Thank you for your attention.